Okay, good morning. Let's see, we're doing 9.2 today. So this chapter goes on for a ways, so 2.5 weeks of classes here. So we're going to get into more challenging stuff, kind of sort of towards the middle. First 3 lessons or so are mostly definitions about circles. And then from 9, say 4 onward, we get a lot of stuff. All right, so here's your homework. Okay. Oh gosh, look at that word. That sounds awful lot like we did last chapter with trigonometry. Well, turns out that this word in math is used for another item in mathematics, and it deals with circles. All right, so a few facts today. Those will be theorems. A few definitions. Those will also be facts as well too. And we haven't done a proof in a while, so let's do one. Well, in fact, we haven't done a proof by contradiction in a really long time. Remember proof by contradiction? Remember the dollar thing? I put the dollar in one of two pockets. I don't actually look in the pocket where it's in. I look in the other pocket. And if it ain't there, then it must be in the other pocket. And that's a proof by contradiction, where you assume the opposite, prove that that leads to a contradiction, and therefore, since it's not true, then the other consequence of that. This works really good when there's only one of two things it could happen. All right, so here's going to be two good examples of a proof by contradiction. So we got a circle, and let's see, it looks like we have a tangent to that circle. That's line M, and that's at point T is the point of tangency. And I'm going to prove that if you do have a tangent to a circle, and you draw a line from the center of the circle to that point of tangency, that ends up being a perpendicular line. In other words, that angle formed between the radius and the tangent line will always be 90 degrees. All right, now that is a really challenging task since there are no angle measurements at all on this circle. Maybe if we had something or an angle measurement, we could get something out of it. So a lot of times when it's really challenging to directly prove something, we immediately go for the big hammer of proof by contradiction, because a lot of times that would be much easier than if we were to directly prove this. In other words, prove that it is perpendicular. So I'm not going to prove it's perpendicular. I'm going to assume the opposite. I'm going to assume that OT is not perpendicular. So proof by contradiction, I'm going to assume that OT is not perpendicular. If OT is not perpendicular, well, O is not on line M, so there must be a line somewhere, a segment, that I can draw from O to M that is perpendicular. Now, when I do this, when I literally do this on the drawing, you're going to immediately say, well, that doesn't look like it's perpendicular. Well, yeah, it's not going to be. Remember, we're making the assumption that OT is not perpendicular. Therefore, there must be a line that is perpendicular. And when I draw that, right, I'll construct it. Therefore, that line, because of our assumption, we're going to make the assumption that that one is the perpendicular portion. All right, so that's our assumption. Remember, we make this assumption that OT is not perpendicular. Once we do that, we reason logically until we come to a contradiction. And when we get to a contradiction, that means that OT must not be unperpendicular, to use a word. It must be perpendicular. All right, so let's see. How would that work? Well, let's see. If OZ is perpendicular, then that would mean that angle OZT is 90 degrees. And we had that one theorem that said that the side of a triangle opposite the largest angle is the largest side. So if the OZ is the one that's perpendicular, then that means that OT is the longest side of the triangle. Therefore, I can make the statement that OZ must be smaller than OT. Now, think about that logic once again. If OT is not perpendicular, then there exists a segment that is perpendicular. I'm claiming that's OZ. Therefore, OZT is 90 degrees, and the side opposite OZT is side OT. So therefore, OT must be bigger than OZ. I just wrote it backwards there. OZ smaller than OT, but it's the same idea. Now, is that a problem? Heck yeah, it's a problem. Think about this. If OT, T is the point of tangency, that means it's a radius. And if OZ is not on the circle, point Z is clearly not on the circle, it's off the circle, right? Well, then that can't be true. It can't be that OZ is smaller. OZ's got to be bigger. That's our contradiction. And our contradiction is that even though if we make the assumption that OZ is perpendicular, it leads us to the fact that OT is actually larger than OZ, and that clearly is not the case. So proof by contradiction, you assume the opposite of the proof, it leads you to a contradiction, therefore your original assumption is wrong, and therefore OT must be perpendicular. So that's my statement there, but Z is not on O, right? So OZ must be larger than OT. Therefore, if that's the case, then OT must be perpendicular. Proof by contradiction. All right, so what do we just prove? We proved this, that if you have a tangent line, line M, and you have a segment from the center of the circle to the point of tangency, T, then that angle formed is 90 degrees. So, oops, sorry, that's what you get. So if a line is tangent to a circle, then the line is perpendicular to the radius drawn to the point of tangency. Now it says radius is also could be a diameter too. All right, so as you're copying that down, put it on pause, and I shall move on. All right, here we go. First shape, first pattern. So this is a corollary to the one that we just proved. I can prove this real quick. Draw a line from the center of the circle to point P, then draw from the center of a circle from A to B. That would be 2 radii. Therefore, you have 2 triangles there. The 2 triangles would be congruent because of hypotenuse leg, the radius, and from P to the center, that would be reflexive property. Therefore, by CP/CTC, AP is congruent to BP. All right. Now, as we do this, the statement might be a little bit, I'm not really happy with the way they state this. This is from the book. So it says, tangents to a circle from a point are congruent. So what does that really mean? Let's see. That means that if you start from a point, in this case, point P, and you draw 2 tangents from point P. Now they can't be lines arrays because they go on forever. So these are going to be 2 tangents that are segments. So from point P to point A and from point P to point B end up being congruent. So that's all it says, right? I can't remember if I assigned the proof as one of the homework questions. I think it did. I did. Well, I just literally told you the proof. Make 2 triangles, prove the 2 triangles are congruent, then call out CP/CTC, and you're done. Okay. So the converse to 9-1, remember 9-1 said that if you have a tangent, then any line drawn from the center to the point of tangency is perpendicular. So the converse to that would be if you have a perpendicular from the radius to a side to a point of tangency, then the line L must be tangent. So once again, to prove this directly would be very challenging. How do you show the line is not tangent? So by proof by contradiction, it ends up being fairly straightforward. So let's see, proof by contradiction. So I'm going to assume the opposite of the proof. So L is tangent to Q. So L is not tangent at point Q. Thus, there must exist, right? There must exist a point Z, right? There must exist a point Z and the radius QZ. In other words, if R is not the point of tangency, then there must be a point of tangency somewhere. And I'm going to claim that that point is point Z. Now, as you look at the picture, clearly it's not. But remember, well, obviously it is. In other words, R and L are tangent. R is point of tangency and L is tangent. But because of the drawing, unless I change the drawing around, but I can't, it's going to be obvious that when I draw this QZ, that, well, that's not a radius. But we make that that's a consequence of the assumption that L is not tangent. So if L is not tangent, then that means that it's a secant. Therefore, it must intersect at some point, and that point would be point Z. All right, why is that a problem? Well, will that mean that QR and QZ are both radii? And if QR and QZ are both radii, and we know that angle QZR is 90 degrees, it says it there, it says L is perpendicular to QR at R. Therefore, since that triangle is isosceles, that means that QZR is also 90 degrees. And that's a problem because you can't have two 90 degrees in a triangle. Therefore, our assumption has to be false. And therefore, well, it's got to be the opposite of our assumption. So we assume that it was not tangent. Well, there's only one possibility. If you're not tangent, then you must be tangent. So that's our proof by contradiction, and that's just the converse to 9-1. So the 9-1 says that if you have a line that's tangent to a point of tangency, then the angle right there is 90. And the converse to that says that if it's 90, then it's a tangent line. Either way works. So if OT is a radius and it's perpendicular, in other words, you get a 90-degree angle at T, then M is a tangent line. All right, some more definitions. Recall from last class, we had the two words inscribe and circumscribe. So inscribe describes the shape on the inside of two shapes. So in other words, the one on the left there, a circle is inscribed in a triangle, and the one on the right there, a circle is inscribed in, looks like a kite. And the second word, circumscribe, we're talking about the shape on the outside. So a triangle, left side, triangle circumscribes a circle, right side. A kite circumscribes a circle. Remember, though, I can show you one shape there with both of those, and I can either be talking about the thing on the outside or the inside, and that's how I choose the word. There's some more challenging vocabulary words. Here they come. All right, so think about this. I'm going to take a segment, and on that segment, I'm going to make a circle that's tangent to that segment. And then I'm going to make another circle that is tangent to that tangent line to the first circle. So in other words, I have two circles that are tangent to the same segment, and we describe that as not in terms of the circle, but in the tangent line. So we say the tangent line is a common tangent. Well, that makes sense. It's tangent to both circles. So it's a line that is tangent to or more circles. You're not going to see three. We're just going to do two. All right, the but here is that, unfortunately, it comes in two flavors. And so you need to keep these track in your head. So tonight for homework, make sure you read over your notes when it talks about these common tangents. They come in two flavors, and these are the two flavors. So think about this. There's two types here. And it's not because I made the circles a different size. So I can make them the same size or different size. So think about this. If I make an imaginary line that connects the centers of the two circles, and then I draw a common tangent, right? I'm going to draw a common tangent. This is one way to draw a common tangent. Either above or below those two circles, you would have a common tangent. Notice the red line does not cross the black line. But there's another common tangent, this blue one, that crosses the black line. Those are the two types of common tangents. We're going to give those names, and the names are descriptive in how they relate to the imaginary black dotted line, or it's not dotted, I drew it solid, the black line that connects the two centers of the circles. Okay, so here we go. So common tangent, right? Flavor one, flavor two. So here's flavor one. Flavor one is where the common tangent intersects that imaginary line that connects the centers of both circles. This one is going to be called a common internal tangent. A tangent between two circles that crosses a line joining their centers. Flavor number one. As always, pause, I'm moving on. Okay, flavor number two. Flavor number two is when that common tangent line does not cross that imaginary dotted line that connects the centers of the two circles. This is going to be called, with the other ones be common internal tangent, this is going to be called a common external tangent. Tangent between two circles that does not cross a line joining their centers. Go ahead and pause it. I'm moving on. All right, so think about this. So if a tangent is a line that touches a circle at only one point, are there other things that can touch the circle at only one point? The answer is sure. You can get a triangle that touches the circle at one point. So therefore, the triangle and the circle are tangent. We are going to focus about two circles. Can two circles be tangent to one another? So the definition of tangent is you are only allowed to touch in one spot. Well, that's pretty easy. Wait, no, I just touched in two spots right there. So I would need to make it look something like this, where they only share one common point. Turns out there's actually another way of making common circle tangents. And that other way, well, let's just find tangent circles first. Tangent circles, now they have to be on the same plane, so that's the coplanar. So those are coplanar circles that are tangent to a line at the same point. Let me go back. You see that line I just drew there in the bottom right? So those are two circles that are tangent to a point, and that point has a line that goes through it. That's what this is saying right here. I should put that picture on this slide. Coplanar circles that are tangent to a line at the same point. So not only are they tangent to that line, they were tangent to that point. I'll go back a sliding in. Turns out, though, there's two ways of drawing that. And so once again, there's going to be two flavors of tangent circles. And I will tell you, these two definitions and the last two definitions can be easily confused. They kind of use the same words. So tangent circles come in two flavors as well, too. I've already shown you the first flavor. So the first flavor and the second flavor are right there. So the first flavor, the two circles touch each other, and the second one, they still touch each other, both times in one spot. The difference is where the line would be, right? So the line on the first one would be, and this is from the book, that's a horrible line they drew right there. The first flavor looks like this. Okay, that makes sense. Two circles touch each other in one spot. They're also tangent to that line L right there, and that line is outside of both circles, right? And so we say that these are externally tangent circles. In other words, the line is on the outside, and both circles, so I'm kind of giving it away, are on the outside. Now that will easily be confused with the second one. So if you think about this, both circles are outside of each other. On the second flavor, one circle is inside the other. So the line is still on the outside. It's still tangent at one point, but these are called internally tangent circles. So when we talk about common tangents, external or internal is really talking about, does a tangent line cross an imaginary line? But when we talk about tangent circles, we're really talking for the internal, external. We're talking about the relationship between the two circles. Are they inside of one another or are they outside? So these are internally tangent circles. And like I said, there's four of those words there. External tangents, internal tangents, internally tangent circles, and externally tangent circles, and they can be easily confused. But the picture's worth 1,000 words. If you have these pictures in your book of truth, and you get a question on this tonight for homework, you can just look this up, and it'll make sense. All right, so for homework, I'm going to just caution you, make sure you read carefully. All those ones, the external thing, make sure you read them carefully. Look at your notes to make sure they match the words, the vocabulary words from how you drew it. So it can be easily confused. Last thing is this is just some interesting trivia. I throw this out every single year. Here's the statement. If you have nothing but congruent circles, so I have an infinite number of congruent circles, take one circle, draw it, and then what I want to know is how many other of those congruent circles can you circle your given one, but they all have to be tangent to one another. In other words, they're only allowed to touch each other in one space. So we say this is how many tangent circles will circle a circle. Start with one circle. How many circles can you put around that circle? But you got to make them tangent to one another. In other words, they're only allowed to touch each other in one spot. Well, your answer is right in front of you. Pick a circle, circle it with other congruent circles, and notice there are 6 of them. And this kind of explains why honeybees like to make their hives out of hexagons, because there's 6 circles that circle a circle. So it has nothing to do with today's lesson other than it deals with circles and tangents. All right. Good luck on your homework. If you have any questions, you're always sending me an email. We're doing really well on that. But if we run into a problem, if this has gone too quickly and you have confusion, we don't have to push forward. We got plenty of time. We're making great progress. We will easily be able to finish sometime in May through the entire book. And then I'm just going to warn you, chapter 10 is going to be a challenging chapter to teach with video. It's all about constructions. You're going to have to watch the video. You're going to have to take really good notes. I will just say our book doesn't describe the constructions as well as I will on the videos. And when you're standing in front of me watching me doing the constructions, it certainly is a pretty good thing. I'm going to try to make the videos using a document camera, and hopefully that works as well too. But just be ready for chapter 10. Remember, you have to have a compass. And if you haven't bought a compass, I would highly recommend buying one of those compasses with a wheel on it for the what opens and closes it. If you buy the ones that are just friction controlled, a lot of kids run into issues with that. Now, if you've already bought one, don't buy another one. But if you have not yet buy one, go on Amazon and just Google compass. And you'll see the kind that have the wheel that open up the two arms of the compass. You can get one for $8, I think. That's the one that you want to get. Okay, so that'll end it for today's video. I will see you to next class, and email me if you have any issues.